Welcome to the Deep Dive. We're your hosts at TalkTensors, where we break down, the latest in machine learning research.
That's right.
Today, we're diving into a really interesting paper called Financial Fraud Detection with Entropy Computing.
Yeah, that title definitely catches the eye. It's all about applying a pretty different computing method to a classic problem.
Financial fraud, huge issue. So what's the core idea here?
Okay, so the paper introduces this new algorithm. They call it CVQBoost. And the really novel part, it's designed for specific hardware quantum computing Inc.'s Dirac-3 system.
Dirac-3, that uses something called entropy quantum computing.
Exactly. EQC. And they're not just talking theory. They've applied CVQBoost running on Dirac-3 to detect fraudulent credit card transactions. It's a very practical test case.
Right, so a new algorithm, new hardware, tackling a real-world problem. How did it stack up? Did they compare it to anything?
They did. They benchmarked it against XGBoost, which, as you know, is kind of the gold standard, a really highly optimized classical method.
Okay, the heavyweight champion.
And the result. Well, that's the exciting part. They found CVQBoost gets pretty much comparable accuracy. So it's just as good at finding the fraud. But the kicker is the runtime.
Ah, the speed.
Yeah. CVQBoost showed like a really significant speed up, especially when the data sets got bigger or had more features. It suggests much better scalability.
And this comparison wasn't just, on paper. They actually ran XGBoost properly.
Oh, yeah, absolutely. They went head to head. CVQBoost on Dirac-3 versus XGBoost running on high-performance stuff, multi-core CPUs, even GPUs using NVIDIA Rapids AI. So a proper tough comparison.
Okay, that's thorough. So the paper lays all this out.
Yep. It details CVQBoost, the EQC paradigm, the fraud detection application. It shows the competitive accuracy, the faster training times, especially as things scale up. They even pushed it with synthetic data, huge sets, up to 70 million samples.
70 million, wow, okay.
Yeah, really pushing the boundaries to demonstrate that scalability point.
Before we get deeper into CVQBoost itself, maybe we should take a step back. This whole idea of boosting in machine learning. Where did that originate? Give us a little history.
Sure. So boosting fundamentally is about combining lots of simple models, weak learners, to create one really strong predictor. Think of it like asking a crowd of people who are only slightly knowledgeable individually, but their collective wisdom is powerful.
Okay.
AdaBoost was one of the pioneers. The basic idea is you train a simple model, see what gets wrong, then train the next model, focusing more on those mistakes, and so on. Then you combine their votes, usually weighted by how well each one did.
And that evolved. The paper mentions QBoost and quadratic formulations. What's that about?
Right. So people started thinking, how can we optimize this whole process of finding the best weights for these weak learners? Quadratic formulations frame this weight-finding problem as, a quadratic optimization task. Minimize a specific mathematical function.
And why is that formulation useful?
Because certain types of hardware are really good at exactly that kind of optimization. And that includes quantum annealers and, relevant here, this entropy quantum computing approach used by the Dirac-3 system. It maps nicely onto the physics.
Okay, entropy quantum computing, you said EQC, it sounds different. How does it differ from, say, the gate-based quantum computers we sometimes hear about, or even classical computers?
It's a fundamentally different paradigm. Digital computers use bits, deterministic logic gates. Gate-based quantum computers use qubits and quantum gates. Annealers try to find the lowest energy state. EQC, specifically in Dirac-3, uses photonics.
Light.
Yeah, basically. It lets an optical system naturally evolve, kind of like a physical process settling down. Higher energy states dissipate, and the system tends towards a low energy configuration that represents the solution to the optimization problem. It's hybrid photonics for the core computation, electronics for control. Continuous variables, not discrete bits or qubits in the same way.
So CVQBoost takes the boosting weight problem and basically sets it up so the Dirac-3 can solve it by settling.
Pretty much, yeah. It formulates the problem using these matrices, J and C. J captures how the weak classifiers relate to each other, like do they agree or disagree. C captures how well each individual classifier performs. The goal is to find the weights that minimize a function based on J and C, with constraints that the weights have to be positive and add up to 1. Dirac-3 is built to find that minimum.
And the weak learners they use, you said they were simple.
Very simple. Just logistic regression, trained on tiny subsets of features, sometimes just 1 or 2 features at a time.
Why so simple?
Well, 2 main reasons, I think. First, it fits the boosting philosophy. Combine simple things. Second, and this is crucial, It helps with explainability.
Ah, the black box problem.
Exactly. If your final strong model gives a lot of weight to a very simple weak learner, say, one that just looks at transaction amount and time of day, you get a direct insight into what the model thinks is important. The paper mentions this potential, recalling older work where simple features were key.
That explainability is huge, right? Especially in finance. You have regulations like GDPR, the right to explanation. You can't just say computer says no.
Precisely. And it's not just regulations. For scientific discovery, understanding why a model predicts something is often the whole point. You want insight, not just a number. Boosting methods, because they're built from potentially interpretable parts, have an edge there compared to, say, deep neural networks, which can be harder to peek inside.
Makes sense. Okay, so they tested this on the Kaggle credit card dataset. You mentioned it's imbalanced.
Extremely imbalanced. Like less than 0.1% of transactions are actual fraud. That's a classic challenge for ML models. They can just learn to always predict not fraud, be mostly right, but useless.
So how did they handle that imbalance in the training phase?
They used a few standard techniques, AdaSY, SMODI, things like that. These basically either create synthetic examples of the rare class, fraud, or remove examples of the common class, not fraud, to give the model a more balanced diet during training.
But they tested on the original unbalanced data.
Yes, that's key. Train on balanced, test on realistic unbalanced data. They measured performance using AUC area under the curve, which is a good metric for imbalanced problems.
And the accuracy results. How did CVQBoost compare to XGBoost there?
Initially, on the raw, highly imbalanced data, XGBoost had a slight edge. But as they applied more balancing to the training data, CVQBoost caught up, and in some cases, particularly with AdaSY and balancing, actually pulled slightly ahead in AUC.
Interesting. So comparable or even slightly better accuracy, especially when you help it see the minority class properly.
Yeah, it shows the algorithm itself is capable of learning effectively.
Okay, let's get back to the speed, the runtime. That seemed like a major claim. How did those comparisons look in detail?
They were quite dramatic, actually. Versus single-core XGBoost, CVQBoost on Dirac 3 started slower on tiny datasets, which makes sense. There's probably some overhead. But around the 20,000 sample mark, CVQBoost became faster, and its runtime scaled much, much better as the dataset grew.
So less sensitive to data size.
Exactly. And interestingly, the actual computation time on the Dirac 3 hardware itself stayed relatively constant. Most of the scaling seemed to come from the data preparation and post-processing steps around it, which grew more slowly. Same trend with increasing the number of features. CVQBoost runtime grew much less dramatically than XGBoost's.
What about against the parallel versions? Multi-core and GPU XGBoost, they're fast.
They are fast, especially on smaller data. But again, it's about the scaling. Multi-core XGBoost hit diminishing returns. Adding more cores beyond, say, 8 didn't help proportionally. GPU XGBoost was very fast initially. But on the really large synthetic datasets, millions of samples, hundreds of features, CVQBoost's runtime advantage became substantial. It scaled almost linearly with the number of features, while XGBoost showed closer to quadratic scaling. That's a huge difference at scale.
Linear versus quadratic scaling. That's night and day for truly massive problems. Did they compare Dirac 3 to other ways of solving that quadratic optimization problem, like classical solvers?
They did. They used solvers like Hexaly and SciPy's SLSQP. For small problems, those classical solvers were actually faster. But as the problem size grew, meaning more weak learners, up to 900 in their tests, Dirac 3 showed better runtime scaling again.
And the solution quality. Did Dirac 3 find equally good answers?
Pretty much comparable, yes, though they noted a tiny potential energy gap for the very largest problems, possibly due to the hardware's dynamic range limitations, something maybe to improve in future hardware generations.
Okay, so summing up the core findings, CVQBoost, running on this EQC hardware, gets similar accuracy to top classical methods like XGBoost, especially if you handle imbalance.
Right.
But its main advantage is potentially massive runtime improvements and better scalability, particularly with large numbers of features or samples.
That's the key takeaway on performance. And combined with that potential for better explainability inherent in boosting, it's a really compelling package.
What are the real-world implications here? Faster fraud models seem obvious.
Yeah, definitely. Training models way faster means you can update them more often, react quicker to new fraud schemes. That could save a lot of money. But think beyond fraud. Any high-dimensional classification task.
Like medical diagnosis from complex data, cybersecurity anomaly detection.
Exactly.
Yeah.
Anywhere you have lots of features and potentially large data sets where training time is a bottleneck. And that explainability angle helps with trust and regulation. Plus, maybe even accelerating scientific discovery, finding patterns in genomics or material science, and getting clues about why those patterns exist. There's also a mention of potential energy efficiency for the Dirac hardware, which is increasingly important.
It really does feel like a potential paradigm shift. Which brings us nicely to our novel notions segment. Where could this lead next? What's a research idea sparked by this paper?
Okay, so thinking about the scalability and the explainability, one idea could be exploring hybrid explainable AI for extremely large datasets.
Hybrid, meaning combining CVQBoost with something else.
Yeah, like what if you used CVQBoost first on a massive dataset? Because it's fast and scalable, it could maybe identify the most important features or relationships, the most influential weak learners.
Okay.
And then you use that information to, say, pre-train or guide the training of a big, deep neural network. The deep network might still capture more complex interactions, but it starts with the better initialization or focus, guided by the insights from CVQBoost.
So CVQBoost does the initial heavy lifting and provides some interpretability, and the deep network does the fine-tuning.
Kind of. You might get faster training for the deep network, maybe better generalization, and crucially, you inherit some level of explanation. You could say the deep network is predicting fraud, and the factors driving this seem related to these simple features that CVQBoost originally highlighted.
That's clever. Using one model's strengths to mitigate the other's weaknesses, what's a less obvious angle on that?
Well, maybe it helps build trust. If the deep network makes a weird prediction, you could cross-reference with the CVQBoost insights. Does it make sense in light of those simpler patterns? It's like having a simpler map to navigate the complex territory. The deep model could be huge for critical applications.
Right.
But again, just brainstorming here, pure speculation for discussion.
Very cool idea, though. Okay, one more novel notion.
How about real-time adaptive fraud detection with EQC?
Real-time adaptation.
Yeah, think about that near constant runtime with the Dirac 3 hardware they observed. What if you could retrain the CVQBoost model extremely quickly? Maybe almost continuously, as new transaction data streams in.
So the model adapts to new fraud patterns almost as they emerge?
Potentially. If the core computation is that fast, maybe you don't need batch training every few hours or days. You could have a model that's constantly learning and adapting in near real time.
That would be a huge advantage against fraudsters.
Exactly. And maybe, going a bit further out, could the entropy aspect of EQC itself be useful? Perhaps unusual entropic states in the system's evolution could flag novel anomalies or shifts in data distribution even before specific fraud is labeled. A kind of early warning system.
Wow, using the physics of the computation itself as a detection mechanism. That's definitely out there.
Highly speculative, of course. Just food for thought. But it shows how different hardware might enable fundamentally different algorithmic possibilities.
Absolutely fascinating stuff. So to wrap up our deep dive today, we looked at CVQBoost, a novel boosting algorithm designed for entropy quantum computing hardware, specifically Dirac 3.
Right. It showed comparable accuracy to XGBoost on financial fraud detection, but with potentially significant runtime and scalability advantages, especially for large, complex datasets.
And this combination of speed, scalability, and the potential for explainability via boosting could have major implications not just for finance, but maybe for science and other data-heavy fields too.
Definitely promising. If you want to dig into the nitty-gritty, we've linked the paper itself in the description.
Check it out. Thanks for joining us on the deep dive.
And it leaves us with a thought, doesn't it? As these new types of computing hardware, quantum-inspired, maybe true quantum, keep evolving, how will algorithms like CVQBoost, built for them, reshape what's possible in machine learning? It's certainly going to be an exciting area to watch.